All right, so I'm going to prove the Pythagorean theorem by using similar triangles. And just because I'm using similar triangles here to prove it, it doesn't mean necessarily it's the best way of proving it. There's actually like a gazillion different ways of proving it. People throughout all of history of math have proven it different ways. A president proved it once. All right, so there are tons of different ways of proving it. And just because I prove it this way, it doesn't mean it's the best way. I'm just saying it that to start. Also, the reason this formula is so important, and you know, when I think about 30 years from now, what's important in geometry, this is the most important result. The reason this theorem is so important, everyone says it's so important, is because it is the distance formula. I mean, every time you have a couple distances, a couple points between them, you use this result. And that gives rise to that analytic part of as far as saying this is the distance between 2 points. This is the result that is used to figure that out. So the theorem states that if you're given a right triangle, and this is only, the Pythagorean theorem is only in context to right triangles. A lot of people think it's, for all triangles, it's only right triangles. And I'm going to draw my triangle a little bit funky here because we're going to prove this result. So I'm going to put it right at the top. There's my right angle, that's 90 degrees. Everyone knows that the theorem states that a squared plus b squared is equal to c squared. You have to know that. Again, c is said to be the hypotenuse. The hypotenuse is defined to be the side opposite the 90-degree angle. So this would be side C. It's across from it. It's opposite the 90 degree. These other sides are called the legs of the right triangle. A and B are legs. So if we're going to write this as a theorem, this would be how we would go about doing it. Okay. So let's get into the proof as to why this thing works. All right, so to start this thing out, I'm going to take this point at the very top, and I'm going to drag it straight on down. All right. And this angle right here, I'm going to define this angle to be 90 degrees. What is that called? This segment from here all the way up, that auxiliary segment, what is that called? It's called the altitude. And in case you ever forget what the altitude is just the height of a triangle. Think of a mountain. If you're going up a mountain, you're thinking the altitude up the mountain. So right here, this is a triangle. The altitude is the distance going up it. So that's the altitude. All right, so we have that. There's also some other important things. If this is 90 degrees right here, we know that this also by default must be 90 degrees. Because those are angles along the same side of a line. So these add up to 180, so that's also clearly 90. Now, it doesn't matter necessarily what angles here and here we let the measure of these angles be. So let's just have that be denoted with one angle arc and this one with two. Now, what's important, though, is that I label those because these angles here and here, they're said to be complementary. Complementary refers to summing up to 90. The reason I know that these angles are complementary here is because 90, that angle at the top, we're looking at the large triangle now, the one along the outside, 90 plus these angles here and here, 90 plus 90, that would give us 180 because of the sum of interior angles of a triangle. So these are complementary. And whenever you're given an angle right here, so if that's, so that we have this measure of this angle here, and we're looking at this triangle, let's call this triangle 1 on the left-hand side. If you're having this be 90 as well, here's this one. Well, this one and this one, they must add up to 90 because 90 plus 90 gives me 180 due to sum of interior angles of a triangle on that one. So this angle and then the other angle would be the 2 angle arc one, because those angles add up to 90 to give 90 plus 90 is 180. And then, so there's that one, and then the complementary angles here are that one. Because 90 plus 90, sum of interior angles are 180 here. And I'm going to call that angle on the right-hand side, I'm going to call that angle 2. Now, these triangles, you know, they're said to partition, break up. They don't overlap each other. They break up that large triangle along the outside. That large triangle on the outside, I'm going to call triangle 3 here. Now, this is a very interesting result here. You actually have 3 triangles now that are similar to each other. And I'm just going to state they're similar, and then I'm going to redraw them and kind of explain why they are. So here, so you have triangle 1 is similar to triangle 2, which is similar to triangle 3. And in particular, we're going to look at 1 and 3 for now. So we're just going to look at 1 and 3 for now. So if we're looking at 1 and 3, and they're similar here by angle similarity. I'm going to show you why. So right here, if I look at triangle 1 here, so triangle 1, I'm going to just redraw it here. Actually, I'm going to do one more other thing too with this diagram above. I'm going to say that this distance from here to here is x, and this distance from here to here, that distance is y. So I'm going to say the distance from here to here, to the base of our altitude, that point, that is x, and this distance from here to here is y. So x plus y is going to give us the hypotenuse. Now, look at triangle 1 here. So I'm going to have triangle 1. I'm going to give myself a little more room. The triangle 1 looks like this. It has the 90. It has the 1 angle arc. It has A. It has the 2 angle arc. It has X. And this is triangle 1. And triangle 3 is the large one. And if I was going to draw that, what I'm going to do is I'm actually going to draw it like this. And actually, I'm going to even make it have the same angles. All the angles are the same here. Look at this. Angle, 1 angle arc, 1 angle arc. Right there. Look at the large one. This is 1 angle arc. This has 2 angle arcs right there. There's my 2. There's the 90. There's the 90. Some people refer to this right here. So these triangles are all similar by angle similarity or angle similarity. They mean the same thing. As long as you have 2 angles, you can specify the last one. I always just call it angle similarity right here. So if we're looking at triangles 1 and 3, they're similar by angle. So by angle similarity right there. So that's the reason right there. Now, if we're looking at this triangle and this triangle, we know that they have the same. What do we know about them? They're all related by a scale factor, but in particular, we also showed that due to that relationship, their ratios are also all the same. So, and let's look at the ratio of their side lengths. So let's look at triangle 3 here. The hypotenuse, so there's my 90. The hypotenuse is x plus y. And you understand this is, so if this was 3 centimeters and this was 2 centimeters, you go 3 plus 2 is 5. So this total distance is x plus y. It's the segment addition. So this is x plus y right here. It's the hypotenuse. And then between the 90 and the 1 angle arc, well, that side is just A. And the last side, it doesn't really matter what that last side is. All right, so this implies if you ever have triangles that are similar, you automatically know that their sides, that their ratios are the same. So it implies ratios of side lengths respectively are the same. In other words, if we're looking at a and x right here, so a to x must be equal to, so a to x must be equal to x plus y to a. So I'm going around this way. In other words, we can say, instead of saying x to a to x, this means the same thing as a over x is equal to x plus y over a. If we're just going to write this in fraction form. And if we were going to cross multiply here, we go a times a is a squared is equal to, now you can kind of see where I'm getting the a squared from. There it is, a squared. So a squared is equal to, and I'm cross multiplying, so a times a is equal to x times x plus y. And also, for the same reason, so by 2 and 3 being similar to each other, we know that this implies that for the same reason, so if we're looking at 2 and 3 here, it's the same reason as all this stuff right here. This implies that, so here's A. If we're going to kind of reflect this thing, that instead of calling it A, there's that correspondence. So that's B. So this would be B here. B squared would be equal to, and instead of calling it, X, you'd have Y. So it would be Y. And then you have this X plus Y, so that it would still be the same thing. So it would be that. So you'd have the same, so you'd have that. Now, what I'm going to do is I'm going to take this equation and this equation, and I'm going to add them together. So what happens is that, so a squared plus, I'm going to take the two left-hand sides, I'm going to add them together, plus b squared is equal to x times x plus y. Plus, so that's the right-hand side on the top, plus the right-hand side on the bottom would be plus y times x plus y. Again, I'm just taking this and I'm adding them together. I'm taking this, I'm adding them together, so it's coming along there. Now, this means that a squared plus b squared is equal to, so you're going x times x plus y, and then there's the y there, but we have the x plus y is the same, so we can take out the x plus y times x plus y, which is equal to, and if you didn't see why this and this are equal to each other, you can think of it like this. You're going x times the quantity x plus y, and it's showing up there, and then you have y times the quantity x plus y, it's showing up right there. Well, that is really equal to, well, if this value is c, this also is c, because that is x plus y, and this distance from here to here, well, that distance is c, because x plus y is equal to c. So this really is equal to c squared. So a squared plus b squared equals c squared. All right. So a squared plus b squared equals c squared. We're looking at here and here. Quad. And that's how you prove the Pythagorean theorem.